Now, nonlinear systems might seem really complicated, but there is something that makes them easier to handle because we can talk about them as something that is almost linear in the right conditions. So now we're going to be talking about locally linear systems. Nonlinear systems that locally, so at a very specific area, can be treated as the linear systems. So we want to go from nonlinear to linear systems. So the first thing we do is we consider x prime equals f and y primes equal g, where f and g are functions of x and y. And we find x star y star being a critical point. What does that mean? That f computed at x and y, x star y star is equal to 0, and the same is true for g. Close to x star y star, we can write a Taylor series for f and for g. And we have that for x and y close to x star and y star, we can write f of xy is equal to f of x star y star plus the first derivative of f multiplied by the distance, so df of x star y star multiplied by the vector x minus x star, y minus y star, and we can add other information. The same thing we can write for g, where in this case we have written capital df, that is a vector, a horizontal vector. We have the derivative with respect to x of f in the first element and the derivative with respect to y of f in the second element. If you multiply this by the vector x and y, you see that dxf is multiplied by x and dyf is multiplied by y. So this is the generalization of the Taylor series to 2 dimensions. But if we write this as a system, what we notice is that because we are next to the critical point, f at the critical point and g of the critical point are equal to 0. So now we're left with x prime y prime being equal to df multiplied by a vector x minus x star, y minus y star, and at the second line, dg x star y star multiplied by the same vector. So we can merge this information and write it as df x star y star and dg x star y star. Both of them are 2D vectors. So we are created a 2 by 2 matrix multiplied by x minus x star, y minus y star, plus other terms. I'm not going to be talking about that because we're assuming them to be small because we're very close to x star y star. So we can write x minus x star, y minus y star, the derivative of this vector, is equal to df computed as x star and y star, dg computed as x star and y star, put it in the matrix, we call it the Jacobian, and we multiply it by the vector x minus x star, y minus y star. And then we have some other small amounts. Small amounts because they depend on the square of the distance. X minus x star squared, y minus y star squared, and so on. So we can focus on this smaller system. But x star and y star are fixed. So the Jacobian computed as x star and y star, this is a fixed matrix. We have gone back from nonlinear problems back to a 2 by 2 ODE system, linear ODE system, because we don't have any nonlinearity anymore. The only difference is that we went from a system of x and y's to a system of x minus x star, y minus y star. We can study now the system VW as a vector prime equals to Jacobian computed as x star and y star multiplied by the vector VW, where we rewrite x minus x star, y minus y star as VW. Let's make an example. We have this nonlinear system, x prime, y prime equals x minus 7 times y plus 3 and y minus 2 x plus y. We can compute the critical points as we did before. So we compute the different factors and we mix and match to have one of each. So the critical points are 7, 2, 7, 7, and minus 3, minus 3. And we can study the linear behavior near either of these points. For example, we can take the point 7, 2. We have f of x and y being x minus 7, y plus 3. So we take the derivative of f. The full derivative means that it's a 2-element vector in which in the first element we have the derivative of f with respect to x, that is y plus 3, and the second element of the vector we have the derivative of f with respect to y. This is x minus 7. We do the same thing for the other equation, that is gxy. It's y minus 2 times x plus y. We take the derivative of g. The derivative being a 2-element vector in which in the first element we have the derivative of g with respect to x, and in the second element we have the derivative of g with respect to y. So now we have a vector that is y minus 2, x minus 2 plus 2y. So the Jacobian is this 2 by 2 matrix where on the first line we have the derivative of f, the 2 elements of them. On the second line we have the derivative of g, the 2 elements of them. And we can compute this at the critical point 7, 2. Some elements get cancelled, so when we compute df, dg, so first line is df and second line is dg, the Jacobian at the critical point 7, 2, we retrieve the matrix that has 5 in the first position, 0 and 0 in the off diagonals, and 9 in the last position. That means that near, possibly really, really close, the critical point 7, 2, our system behaves as the linear ODE system associated with the matrix 5, 0, 0, 9. So we go from a nonlinear system to a system that near 7, 2 behaves like x minus x star, y minus y star prime equals the Jacobian at 7, 2, 5, 0, 0, 9 times x minus x star, y minus y star. Now, we can find the eigenpairs of the Jacobian at the critical point, and we find that the two eigenpairs are 5 associated with the eigenvector 1, 0, and 9 associated with the eigenvector 0, 1. So near, again, all of this is true near the critical point. We have the information that the behavior of the system is one of an unstable node. How long does that last? How far can we go in this information? We don't know, because the further we go, the more important the nonlinear terms that we threw away will become. But if we go close enough, then that is a very important information. That is a good representation of the system. We can make another system, another example. We look at x prime y prime equals to y plus x to the third and minus x plus y to the third. If we can solve for this, x is equal to y is equal to 0 is a critical point. We can compute the derivative of the first line with respect to x and y, the derivative of the second line with respect to x and y, put them together and compute them at 0, 0. So the Jacobian of this system, computed at the critical point 0, 0, is the 2 by 2 matrix 0, 1, minus 1, 0. We have seen this matrix already. This gives us a center. But if we change our nonlinear ODE system, if we change it to polar coordinates to understand if we're indeed circling around 0, 0, we can write that the derivative of r squared is 2 times r prime. But the derivative of r squared is also d over dt of x squared plus y squared. That is 2x x prime plus 2y y prime. We have x prime and y prime given by our ODE, so we can write 2 times x plus y plus x to the third plus 2y times minus x plus y to the third. If we sum these two up, we retrieve that it is 2x to the fourth plus 2y to the fourth. This obviously bigger than 0 because it's a sum of two things that can only be positive. So we retrieve that 2r prime is something that is strictly positive, but r is strictly positive, so r prime is strictly positive. What does that mean? It means that if we have shifted back, if shifted from the xy coordinates to the polar coordinates, the derivative of the distance from the center is constantly increasing. That means that the approximation that we built doesn't work, because on the linear approximation we have the information that the critical point was a center, but if we did our math correctly, we found out that it wasn't. It was an unstable spiral. Why does this happen? It happens because in our linear approximation we found two eigenvalues that are exactly imaginary. If we perturb this information a bit, that means if we move these two eigenvalues a little bit, we don't know if they're still on the imaginary axis, purely imaginary, or if the real part appeared. So if they have a real part that is positive or a negative real part. In this case, the perturbation was such that it just changed them a little bit towards the real positive real part. That was not clear from the linear approximation. So when we're doing linear approximations, we have to be careful that a little perturbation of our eigenvalues would not change the solution. If changing a little bit the positions of our eigenvalues changes the type of eigenvalues that we are, then linear analysis is not enough. Let's look at some bad cases and good cases. If you have lambda 1 and lambda 2 real and different, then swiggling them around a little bit will keep them being real and different. So our linear approximation is good because it gives us important information about the behavior of the system that can wiggle the way without losing information. A bad case if it's lambda 1 and lambda 2 are equal and real with corresponding eigenvector. So only one associated eigenvector. In this case, we have to go, in the linear case, we have to go to generalized eigenvectors and so forth. But if you think about it, swiggling them, changing, adding a small enough perturbation might keep you in the situation in which lambda 1 is equal to lambda 2, or move them away from each other on the real axis, so they are now different and real, but they can also start moving in the vertical direction, and now they are complex. So this is a really bad case because a small perturbation can keep the status quo, but also dramatically change the situation. Let's look at another situation. A good case, we have lambda 1 is the complex conjugate of lambda 2, with the real part of lambda 1 being different than 0. A small enough perturbation will keep the situation. They're both complex and the real part is different than 0. What if they're complex but the real part is equal to 0? Then a small perturbation can keep the situation in which the real part is equal to 0, or could add a real part. This is the example that we just saw. A small perturbation can add a real part to the eigenvalues. And now we don't know anymore if it's stable or unstable situation. So let's look a little bit longer to the bad cases. In a case in which we have lambda 1 equal to lambda 2, real, and repeated eigenvectors, a little perturbation can bring us to three different cases. We can still have that lambda 1 is equal to lambda 2, or we can have them being different and real, or we can have them complex. What happens is the stability of the system doesn't change, But we can go to a situation in which we don't have repeated eigenvalues, or we have a spiral. So we take this situation and swing it a little bit, and drastic changes can happen by having the appearance of a spiraling behavior. On the other hand, what we know is that the stability of our linear approximation is correct. What happens if we have the bad case that lambda 1 is purely imaginary? A little perturbation. Oh, sorry, this slide is not correct. A little perturbation can add something on the real parts. So we still have the information that there is an imaginary component. So the behavior is circling around the center, but we don't have information about the stability. Stability is not given in this case. If we want to notice stability, we have to do some extra steps. Let's look at a full-blown example of a nonlinear system. We have our 2D nonlinear system being the derivative of the vector xy equals to x squared minus 4y and x times y minus 1. First step, we find the equilibrium. We need to satisfy both right-hand sides equal to 0. The first one gives us x squared equal 4y. The second one gives either y equals to 1 or x equal to 0, giving us free equilibria plus or minus 2, 1, 0, 0. Then we study the linear approximation at each of these equilibria. Let's go for it. We compute the Jacobian, the derivative of f, and the derivative of g with respect to x and y. So we have the matrix 2x, 4, y minus 1, x. At the first equilibrium, the equilibrium 2, 1, our Jacobian becomes 4, 4, 0, 2. So the nonlinear system at 2, 1 can be approximated by the linear system v prime w prime equals 4, 4, 0, 2 times the vector vw. This has eigenvalues 4 and 2. It's a stable node. That means it's a good approximation. We can compute the eigenvectors associated with these eigenvalues, and that will give us information on the behavior of the system. We can do this for every single of the free equilibria and find out if they're good approximations.